Well, hello everyone, and welcome to APC Mechanics 2019 Set 1, Question 3, which you very quickly can see is the dreaded rotation problem. This one I think is doable, there's little hard parts in it, and it does have a part at the very end where you could grab a couple of points if you've read that far and you haven't just given up because it's a rotation problem. So take a look at the description of what's going on here. And note a couple of important things. We've got this motor-driven wheel here, which is turning. It's touching the platform at a distance d from the axis of rotation. Right? The platform has a rotational inertia, which we're calling I sub p. Right? Wheel has a radius little r. And then here's something important. Platform starts at rest. Wheel exerts a constant horizontal force of magnitude F, tangent to the wheel. If the force is constant and the distance from the axis of rotation to the point of application of the force is constant, then that means the torque is also constant. And when we have constant forces and constant torques, right, we end up with uniform accelerations and uniform angular accelerations. And when we have a problem that employs uniform accelerations or uniform angular accelerations, we should be thinking kinematic equations. Right? So they kind of gave you that little hint there by telling you it was a constant horizontal force. The other thing that's important to pick up is that during time delta t, the wheel stays in contact without slipping. Right? So this is a perfect contact without slipping. This is, of course, how it can exert a constant horizontal force. So, first part of the problem, derive an expression for the angular speed omega p of the platform. If you go back, that's right after it's been rotating for a time delta t, which means that we know the time, right, that the force has been applied. We also know that the platform started at rest, but to do any kinematics equation problem, we need to know three things. We need to have three givens. So we've got the initial angular velocity of the platform is 0. We have the time as delta t. So we need one more thing. And as they show you down here, the one more thing you can get is the angular acceleration. And so if we look at what the wheel is doing to the platform, right, torque equals I alpha. They say the torque is just the force times d. If we go back to the diagram, right, d is the distance from the axis of rotation to the point of application of the force. Note it also said tangent to the wheel, so technically this is really FD sine of 90, but the sine of 90 is 1. Right? And this is the rotational inertia of the platform times alpha. So we can solve for alpha. So using those three things, the initial angular velocity is 0, the time is delta t, and the angular acceleration is FD over I sub p. We can choose the first kinematic equation and solve for the final velocity, which would be the omega p. Make sure you're using their symbols here. Right? Don't use some other, don't use an R or don't use just an I, right? Or a T. Use their symbols. Right? So 2 points there, basically. 1 point for figuring out that you need to find the acceleration and doing that correctly, and then 1 point for using the correct kinematic equation. Now we want to know the kinetic energy. This is fairly simple, even though it's worth 2 points. Notice your answer has to be in these terms. Right? So these are the only variables that are allowed. So since rotational kinetic energy is 1/2 I omega squared, right, and omega sub p is not one of the allowed variables, right, you need to plug in the omega p you got from the previous part, square it, and simplify. Now I will say this, there is an error in this key. Anyone see the error? Yes, they did not use I sub p here, here, and here as they should have. As I just got done telling you, use their variables. All right, so be specific. Would they take a point off? I don't know. I mean, not when their key's written this way, but, be technical. Don't make them think and guess what you're thinking. So now we want the angular speed of the wheel at that point when the platform is moving at omega p. So this is where that last little sentence comes in the problem statement, which is that the wheel stays in contact with the platform without slipping. The only way that's going to happen is if the outside of the wheel is moving the same as the platform. Right? It's got to be moving the same speed. If it wasn't moving the same speed, it would be slipping. Right? Imagine the wheel going faster than the platform, or the platform going faster than the wheel. Right? So that's what it means to say that it's not slipping. So therefore, we can relate the linear speed of the platform at that point to the linear speed of the outside of the wheel. And as you hopefully know, we can convert the linear speeds to rotational speeds by using v equals omega r. Personally, this isn't the way I would write it. I would write it as omega p rp and omega w rw, but you know, you get the idea. And then you have to plug in the correct variables in this case, because you want your variables expressed in these terms, which is d, r, and omega p and physical constants, which don't really come into play here. So we plug in a d for the distance where the platform is, right, where the wheel is, right? And this is the r of the wheel, right, because it's the outside of the wheel we're talking about, and there's our answer. So here's the complex part. So now the platform is spinning in omega p, right? And they take off the motor-driven wheel, so it's just going to rotate. And there's no forces of friction here, so it's just going to rotate perfectly and keep rotating. Student takes a disc and holds it right above it, drops it, falls onto the platform. They connect together and start rotating together. So part D, they want to know what will their final angular speed be. So hopefully you're looking at this and you're saying, okay, with two discs now spinning instead of just one disc, the rotational inertia has increased. In fact, it's doubled. And therefore, the angular velocity would have to decrease. Now, if you really think about it, you might even have an answer here without writing anything out, right? However, the question says derive an expression, which means you need to show some work. So unfortunately, although you might be able to figure out this answer in your head, you got to show your work. And notice it's got to be in terms of omega p and IP and physical constants. So this is two things connecting to one another. Hopefully you're seeing this as a collision. And how do we analyze collisions? Conservation of momentum. Since these are rotating objects, it would be the conservation of angular momentum. So notice your first point is for recognizing that you can use conservation of angular momentum. Initially, only the first platform is rotating. Afterwards, they are rotating together. So you'll notice the first one here is I. Again, I don't know why they should use IP, but they use I, right? An omega of the platform. And then here, note, this is the important thing, now there's two that are rotating the same, so it's I plus I, if you will, or 2I, right, times omega F, and so you get 1/2, right, what it was before. We did something like this in class, right, but this one's a nice one. I mean, again, it's a little tricky in that you might think through the answer in your head, right, but that'll only give you 1 point, all right, you need to derive the expression, so need to show your work. All right, so they do this a bunch of times, right? And they graph this, right? And they do it a bunch of times by varying the initial angular velocity, I believe, of the disk, right? And then they calculate or measure, if you will, the final, right? And then they graph it. And they graph it each time, okay? This would actually make kind of a nice lab to do in class. And they want you to draw a best fit line for the data. Notice that it is linear. Okay? This is just 1 point here, but again, you can have a straight edge on a test, you can have a ruler on a test, and so you can draw it, make sure it's nice and straight. Personally, I would have extended it back through the axes, but, you know, I probably would have hinged it at 0, 0, because if the first one's not moving and you drop the second one, it's not going to start rotating. Right? So it should go through 0, 0 logically, but, you know. Note here, they have several points below and several points above. And that's what they'd really be looking for to see if it's an appropriate best fit line. They give you a little wiggle room here, right? But that's just one quick point, but make sure it's linear and make sure you have some points above and points below. Try to average them out in your head. So as I've told you countless times throughout the year, whenever they do on an AP test, lab-based problem, and you graph a linear graph and you draw a line of best fit, the next question they ask you almost always has something to do with the slope of that line of best fit. How do you find the slope of a line of best fit? Well, you pick 2 points from the line. Maybe a nice 2 points, like, you know, something like maybe this point, right, which goes right through the crosshairs, and then pick a second point. You can use 0, 0 if you want, if you decided to draw yours back through there. But if you do, you should show that, right? Don't just put in 0 and not put in 0, 0 in your head and don't show them that, right? They are looking for you to find a slope using 2 points on your line of best fit. Now notice what this slope would tell us, right? Rise over run. It would tell us the change in omega f over the change in omega I. Right? It would tell us the change in the final angular velocity over the change in the initial angular velocity. Now keep that in mind as we work through this next part. So I want to know the rotational inertia of the unknown object, which they're calling I sub u, as opposed to I sub p of the platform. And so we're going to use conservation of angular momentum again. Right? And here it is written out. Notice you can't combine these together anymore because it's not the same object. And then they solve this for what they're looking for, IU. And you end up with this. Well, notice this little part, right? Omega I over omega f. Is that the slope? Nope. That's the inverse of the slope. Right? Slope here is rise over run. I have never seen them ask a question like that where you have to pick that up. So good on them. They came up with something original. Right? This is the slope here would be change in omega f over change in omega I. So when you find that slope, oops, let's go forward. When you find that slope, you got to invert it. Right? If you're looking for where they got those numbers. Right? So this is really the change in omega I, which is the horizontal axis. This is the change in omega f. Right? Notice they picked 2 nice points. They plugged in the 3.1 kilogram meters squared. You got that from the problem somewhere. Oh, I know it was in the problem. I looked it up earlier, but it's in the problem. Right? This 3.1 kilogram meters squared. You plug it all in, right? And you get your answer. Now, this is a 2-point problem. And to me, this is way harder than a 2-point problem. I would probably make this 4 points myself. I would think you would have the 1 point for the proper slope, 1 point for using conservation of angular momentum, 1 point for plugging it in, everything in the right place, 1 point for getting a legitimate answer. So, you know, the quality of your slope. But hey, they made this only 2 points here. Notice they say in the notes you can use 0, 0 here, but you should show it implicitly. That means you should show it here. Or if you're finding your slope off to the side, right, you should show it there. Don't just assume they're reading your minds. Again, key here, you are making a linear graph. They ask you to draw the line of best fit, so the very next question has something to do with the slope. Doesn't mean it is the slope, but it's something to do with the slope, right? So that always gives you a kind of a direction to work through. Last part, this is the 2 points that I think you could get even if you didn't get anything else in the rest of the problem. Right? So kinetic energy of the splitting platform before the object is dropped is Ki. They want to know, what's Kf going to be? What's it going to be after they drop the object on there? Well, hopefully you realize that the final kinetic will be less than the initial kinetic. Why? There is no reason to believe this is an elastic collision where kinetic energy is conserved. I mean, you're dropping two things, they're hitting one another, there's going to be some energy dissipated. Right? And that's really the answer they used, although they used the terminology kinetic energy will be lost. I would much prefer you would say kinetic energy would be dissipated during the collision, but, you know. And so you need to give a justify here, right? So you need to explain your answer. And notice the explanation isn't long. They're not looking for, you know, a 5-paragraph essay here, right? They're looking for something quick. It's 1 point. But notice you can even get a point if you just click the right box here, right? You just put an X in the right place. Sorry, over here. Right? You can get the right answer. So again, final kinetic is initial. And notice they didn't ask you to prove it. They didn't ask you to derive it. Right? So if you spent your time showing that it would be smaller, right, you kind of wasted some AP test-taking time, right, when you can probably think through the answer a little more quickly. So be careful when they say justify. Yeah, they would take a mathematical justification, but you know, if you can get at it a little more conceptually, which after a year of AP1 or honors physics that you all had leading into this, right, you hopefully can do, then you can get to your answer without using as much time. So I hope you've enjoyed these 3 very long videos going over this first set of 2019 APC mechanics problems that they actually used on the AP test itself.